In the last video, we took a giant step closer to building a Brickout game with a player-controlled paddle that can strike our bouncing ball. Now we're going to see how to both simplify and scale what we have by using some object-oriented programming and pygame.Sprite and Group classes. This will enable us to add bricks with just a few lines of code. This is Brickout 4.0. All code from this video series is available in my GitHub repository. There's a link in the description. Let's identify all of the variables and code that produce our bouncing ball. We have our surface, which happens to still be called square, and we have x, y, dx, and dy variables. Before the game loop, we have assignment statements giving x, y, dx, and dy initial values, and creating the surface, setting its color key, and drawing a circle. In the game loop, we have some code that updates the circle, adding dx and dy to x and y, respectively, and boundary checking. There is boundary checking with the paddle as well, but I'm going to comment that code out temporarily. Don't worry, we'll get it back shortly. And finally, there's drawing code, in which we blit the circle to the screen. Encapsulating all ball data and operations into one data type will both simplify our game and make it easier to modify and extend. This is a perfect situation for an object-oriented approach. Let's collect our ball code into a class called ball. I've drawn a UML class diagram for ball. I will implement that, keeping the diagram on screen as a guide. Let's define a class called ball under our imports. Our ball will have 5 fields, the surface, which we will call image, and ints x, y, underscore dx, and underscore dy. The convention in Python is to name private class members with a leading underscore. Only dx and dy will be private, for reasons that will become obvious later. The init method is the setup code. It will take the surface size as a parameter, as well as the values for x, y, dx, and dy. Here we'll create the surface, set the color key, draw the ball, and initialize the x, y, dx, and dy fields from the parameters. Just a refresher on Python class definitions. These are instance-level methods, so the first parameter is self, which is the object receiving the message. We must prepend all fields with self dot. I can't tell you how many times I've forgotten to prepend fields with self dot, especially when I was first learning Python. If you have an error, check that first. A ball will also have an update method that takes the screen as a parameter. This will be our update code from before, with small changes to reference the fields of the ball object rather than the variables from the earlier code. And finally, a ball will have a draw method that takes the screen as a parameter. This will simply blit the ball's image to the screen at x, y. Now, in the game code, we'll make a ball object and send it messages. I'll annotate a variable ball of type ball. In the asset setup area, I'll instantiate ball with ball equals ball open paren, 25, that's size, 100, 100, that's x and y, and 5, 5, that's dx and dy. I've decided to make the ball half the size it was before. You can, of course, give it whatever size, starting location, and velocity you like. In the game loop, after we process events, I'll send the ball the update message with ball.update screen, and in the drawing area, I'll send it the draw message with ball.draw screen. And if I run it, my program looks basically the same, except again I've made the ball smaller and temporarily removed the ability of the paddle to hit the ball. You can see how the game loop is greatly simplified by removing the ball code and replacing it with messages sent to the ball. Another advantage of encapsulating all of the ball code in a class is that it's easy to modify and debug anything that's going wrong with the ball because the code is all in one place. It's also easy to play around with the ball parameters, size, location, and velocity, simply by changing the parameters to the initializer. But here's the massive advantage. I can easily make lots of balls without adding a lot of variables. Let's see that in action. I'll annotate a list of ball objects, balls, and instead of creating one ball, we'll create a whole list with balls equals the empty list, and then for I in range 10, balls.append, ball, open paren, and we'll pass in some random sizes, starting locations, and velocities. And in the update area for ball in balls, ball.update screen, and in the draw area for ball in balls, ball.draw screen. And if we run that, 10 balls of random sizes and velocities bounce around the screen. Each one has its own surface, its own location, its own velocity, but they all behave in the same way. We can make 1 or 10 or 100, as many as we want. This is a powerful feature of object-oriented design. I'm going to set that back to just one ball. The ball class that I created is a sprite, a graphic that moves around independent of the background. A sprite is composed of code that we already know how to write, collected into one class. Pygame has a class called Sprite, which is a generic version of a sprite that we can use or subclass for more specific behavior, like our ball bouncing behavior. We don't strictly need to use it, as you can see, but the pygame.Sprite class is hooked into other pygame functionality, such as more efficient drawing and powerful group management and collision detection. So it makes sense to make our ball a subclass of Sprite and tap into those advantages. We will just need to rewrite it slightly to do that. First, I'll put pygame.Sprite in parentheses after my class name in the class definition. That is how you subclass in Python. Next, I'll invoke the superclass init method at the start of the init method with super open close paren .init. That ensures all the superclass parts of the object are properly initialized. The pygame.Sprite relies on two fields, image and rect. These fields are used for drawing and collision detection. The image is a pygame surface, and we already have that. Let's talk about the rect field because it's pretty cool. In our game, we position our image on the screen with our X and Y fields. And when we check boundaries, we use X and Y combined with the width and height of the image. From now on, we're going to use the sprite's rect field, a pygame.Rect, instead. Rect is a pygame type. It contains position and size information, so it is used to position the image, and it will also make boundary checking easier. We will set the rect field after we create the image by getting the rect from the image with self.rect equals self.image.getRect. That rect is the bounding rectangle of the surface with a top left coordinate of 0, 0. We need to set the top left to xy. Pygame will use that coordinate to blit our image when it draws our sprite. We can do that with self.rect.topleft equals open paren x, y. The method we need to override is update, and we've already written that, but now we can make the code much more readable by removing our x and y variables and using the rect, which has attributes for left and top, as well as right and bottom, among others. So first, to change position, we'll add our dx and dy fields to self.rect.left and self.rect.top. In the boundary checking, we can check the rect's left attribute against the left side of the screen, and we can check the rect's right attribute against the right side of the screen, and we can use those attributes to position the sprite as well. No more arithmetic with the location and size of the sprite. And finally, we don't need a draw method, as long as we define the image and rect fields, and we put our sprite in a group, which we'll get to in a moment. So I'm going to delete that. Now the ball class is a proper subclass of sprite, and we can tap into that sprite functionality by putting the sprite in a group. A group is a collection of sprites. So in our game, after creating the ball, we'll create a group to put the ball in. I'll call it ball group and annotate it as pygame.Sprite.Group. And I can create it and then add the ball, or I can create it passing in a ball or a list of balls. I'll create it passing in the ball. Down in the game loop, I'll send the update and draw messages to the ball group rather than the ball. The draw method needs the screen argument because it needs to know where we're drawing. The group's update method doesn't require parameters, but any we pass in will be forwarded to each sprite. And if I run it, my program works as before. So that may not seem like a win, but this is a huge improvement because of all of the pygame functionality that is open to us once we use sprites in groups, including massive collision detection improvements and more efficient drawing. Now, I'm going to kludge the paddle collision detection back into the game temporarily, without making a paddle sprite, because I don't want you to feel like we're going backwards. I'll uncomment that statement. Pause the video, take a look, and see if you can rewrite it using the ball's rect and dy fields, and then come back. How do you do? So I have if ball.dy greater than 0 and ball.rect.bottom greater than or equal to paddle y and ball.rect.right greater than or equal to paddle x and ball.rect.left less than or equal to paddle x plus paddle.getWidth. Then ball.rect.bottom equals paddle y and ball.dy times equal -1. Right now, our game is in a transitional phase where we've started to implement components as sprites, but we haven't finished yet. And so I violated the information hiding principle by accessing private fields of my ball sprite to get this done. That's why this is a temporary kludge. We really want to implement all of our visual moving game components as sprites and use the group's collision detection abilities to check for collisions. That will be your homework after some more practice. First, we're going to make bricks. So let's put the bricks into the game. I'm going to make a super simple brick subclass of sprite with only an init method. For parameters, I'm going to take a surface because bricks of the same color can share a surface. Remember, the surface gets copied to the screen when we draw. There's no reason for each brick to have its own surface if they're all the same. It's also going to get x and y coordinates for the brick. I'll then set the image to the surface, get the rect from the image, and set the top left of the rect to xy. That's it. Now, down in the game, we'll create a group for our bricks. I'll call it brick group, and I will initialize it without passing in a parameter. We'll add bricks to it in a loop. I'm going to add some constants and variables so I can modify the way the bricks look with just a few changes. So I'll define numBricks as 10, offset, that's half the space between the bricks, as 2, and brick height as 20. I'm also going to create a list of brick colors, which are a muted red, green, blue, and yellow. Then I'll set brick width to the width of the screen divided by the number of bricks and subtract from that 2 times the offset. I'll then set x to the offset and y to the brick height, and now I can loop. I will loop over the colors. Each color represents a row. For each color, I'll create a brick surface by passing in the brick width and height, and I'll fill it with color. That surface, again, can be shared among all bricks in that row because they're all the same color. So now I'll generate the bricks in that row. For I in range numBricks, and then I'll write brickGroup.add, that's the method for adding a sprite to a group, and I'll create the brick surf, xy. Then I'll change x to the coordinate for the next brick width plus offset times 2. That inner loop executes numBricks times, drawing one complete row of bricks. Outside of the inner loop, but still in the color loop, I'll update x and y so I can draw the next row the next time through the inner loop. Y plus equals brick height plus offset, moving y down for our next row, and x equals offset. I'm resetting x back to the beginning of the row. A new surface is created and filled with the next color, and the inner loop will execute again. That creates all of my bricks and puts them in the brick group. Down at the bottom of the loop, I'll draw the brick group before I draw the ball group with brickGroup.drawScreen. And if we run that, we can see the bricks, but the ball just bounces against the top of the window as if they're not there. So one more upgrade today. We'll check for collisions between the ball and the bricks, and this is so easy because we're using Pygame Sprites and Groups. After I update the ball, I'll write if pygame.Sprite.Sprite collide open paren, ball, brick group, true, colon, ball dy times equals -1. Okay, you might have noticed a little information hiding kludge there as well. Don't worry, it is just temporary. So what is that? That's a function that will check for a collision between a single sprite, the first argument, in our case, ball, and a sprite group, the second argument, in our case, brick group. And if we pass in true, the element that the sprite collided with from the group will be removed from the group. So any brick collided with will no longer be in the group brick group, so it will not get drawn or checked for collisions with the ball. But we want more than that. We want the ball to bounce. The sprite collide function returns a list of sprites from the group that were collided with. I don't need to do anything special with those sprites though. I just need to know if there were any. So if sprite collide, an empty list will evaluate to false. But if there's anything there, that will evaluate to true. And if so, that means the ball hit a brick, and I'm bouncing the ball with ball._dy times equals -1. And when we run that, our Brickout game is really taking shape. There's still more to do. But I hope you agree that we have something pretty cool here, and it was not very difficult. So for homework, you knew there would be homework. Collect up that paddle code and make it a subclass of Sprite, and integrate it into the game. If you get stuck or want to share your successes, please drop a comment below. And as always, have fun and keep coding.